Okay, so it's a great pleasure to have Netta Engelhardt here from MIT to talk to us today about free energy from replica wormholes.
All right, thank you, Jamie. And I'm going to spend about 2 minutes trying to remember how to set this up so that I can share a screen. Just give me 1 second. All right, is this working?
Yeah, looks good.
Yeah. Okay, great. All right, well, thank you all for the invitation. Thank you, Jamie, for the introduction. It is very nice to see all these familiar faces, and I hope everyone's having a good apocalypse. So this talk is called Free Energy from Replica Wormholes, which is the same as the title of this paper that came out last month with Sebastian Fischetti and Alex Maloney. Now, replica wormholes have been showing up a lot on the archive in the past year or so, and they usually show up in the context of these new calculations of the von Neumann entropy from the gravitational path integral. Now, these replica wormholes are going to come from they're going to be a little different. They're coming from a somewhat different replica trick, but nonetheless one which is being computed via the gravitational path integral. And so this is a different replica trick, which nonetheless is still giving us replica wormholes. And this is the replica trick that computes the generating functional or the free energy. So the unifying theme here is understanding these contributions of the replica wormholes to the gravitational path integral. And this is a different approach in the sense that it's computing a different observable using a different type of replica trick. So the beginning here, of course, is with the black hole information paradox. So here I've drawn the canonical picture of the evaporating asymptotically flat black hole. And the past year, it's a little over a year at this point, has seen really a lot of progress on the black hole information paradox. Now, of course, we don't research, we don't investigate the black hole information paradox for its own sake. We investigate it because we are interested in quantum gravity. We're interested in what the resolution implies for perturbative and non-perturbative quantum gravity. So of course, the end goal here is that we understand the black hole information paradox better, means we understand quantum gravity better. And that's one of the things that I found have been incredibly exciting regarding the progress of the past year, which is that these insights have actually given us, from these developments on the black hole information paradox, have actually started to teach us more about gravity in general. And this is, of course, what we were hoping for, and it's very exciting to see it being realized. Now, what do I mean by teaching us more about gravity in general? I could mean a lot of different things, but given the title of this talk, you probably guessed that what I mean is the inclusion of replica wormholes in the von Neumann entropy replica trick. And now, replica wormholes, or rather Euclidean wormholes, are not new objects. They've been known for quite some time. But the inclusion of replica wormholes in the von Neumann entropy replica trick has certainly given us a new lens with which to look into these old insights about Euclidean wormholes and ensembles in gravity. I'm referring back to work by Coleman and Giddings and Strominger, etc. So what I'm going to do is I'm going to begin by reviewing some of these developments on the inclusion of replica wormholes in the von Neumann entropy. This won't be the majority of the talk, don't worry. I'm sure many of you have seen many talks about this, potentially ad nauseum at this point. But I do want to set the stage with the review of this because it's going to be quite important just to have an understanding of the intuition and the motivation behind our investigation. And then I'm going to discuss this new work on replica wormholes and the free energy with Sebastian Fischetti and Alex Maloney. So this is the outline. First, I'll do some review, as I said. Then I'm going to talk relatively formally about what we mean by the replica trick for the free energy and why it's relevant to the current context. Now, that's all going to be relatively broad and just an explanation of why we actually need to do this replica trick rather than what we might have thought we would want to do. And after that, to ground this and show that, no, this replica trick really is important and it really does receive contributions from replica wormholes, I'm going to do an explicit calculation of the free energy in JT gravity at low temperatures. Now, I say I'm going to do an explicit calculation. Of course, I'm not going to put you through doing the calculation, but hopefully I'll give enough of the details that it'll be clear what we did. And I'll finish up with some summary, comments, and future outlook. So without further ado, let me begin with a review of the developments about the page curve and the black hole information paradox. And I'll be relatively brief here. So the initial results that started some of this new excitement on the black hole information paradox found that we can force an ADS black hole to evaporate by coupling it to an external reservoir. So you take some, imagine we're working with JT gravity, you take some two-sided black hole, and you might imagine coupling one side to some external reservoir at a lower temperature. And then you can use the quantum extremal surface prescription to compute the entropy. And that results in a unitary page curve, which roughly looks like this. So this is a unitary evolution of the von Neumann entropy as computed by the quantum extremal surface prescription, as opposed to what you would get if you used Hawking's approach, which would have given you this non-unitary entropy for the radiation. So this was the basic idea earlier of the earlier developments. Now let me quickly remind you of the quantum extremal surface prescription, since it's very difficult to move on to the developments in replica wormholes without discussing this first. So this is a prescription which is a generalization of the classical formulas by Ryu Takenagi and Hubini Rangamani Takenagi, where you extremize a quantity called the generalized entropy. So you want to compute the von Neumann entropy of a reduced density matrix or density matrix in the boundary theory. And this is a holographic calculation for that. You take the area of a 4G H bar plus the von Neumann entropy on one side of a surface chi r. So here is an example. R is some subset of the boundary. This is not in JT gravity, since the boundary in JT gravity is one-dimensional. And here is some surface chi r. And the idea is that you extremize this quantity over all possible surfaces chi r. The surface that extremizes this quantity as gen is the quantum extremal surface, or a quantum extremal surface. And if you have multiple such quantum extremal surfaces, you pick the one that minimizes the generalized entropy among the extrema. So again, this is for a higher dimensional system. This is the quantum extremal surface, and you compute the von Neumann entropy on one side, specifically the side that is bordered by R. So this is a lightning review of the quantum extremal surface prescription. Now, the relevance to this work, of course, is that the unitary page curve is computed by the quantum extremal surface prescription. So the point that we'll need for the rest of the talk is that as you evaporate the right side of the black hole into some lower temperature reservoir, what happens is that at late times, there is a new quantum extremal surface. So here, this chi sub L is the quantum extremal surface that corresponds to the left side, which is unaffected by anything we've done to the right side. And this here is the quantum extremal surface for the right side, which changes as we evaporate the right side into the reservoir. Now, at late times, there's a new quantum extremal surface that has no classical counterpart. Now, what do I mean by that? Well, if you just look at this formula here, you might suspect that a quantum extremal surface only exists near a classical extremal surface because we're working in perturbative quantum gravity, and A over 4G should always outweigh S out. Now, one way of seeing that this is not necessarily the case is that, of course, we're looking for an extremum, which means that we're looking at the divergence of these. And even if A over 4G outweighs S out, that doesn't mean that their derivatives have to. So what ends up happening is that we end up getting a new quantum extremal surface, not anywhere near a classical extremal surface. And this actually dominates the quantum extremal surface prescription. And the effect of this transition, the effect of including this new quantum extremal surface, is in fact unitarity, or this unitary evolution of the entropy as computed by quantum extremal surfaces. Now, this is of course the entropy of, I should say this is the entropy of the right side, but we might be interested in computing the entropy of the radiation, which leads us to this so-called quantum extremal island formula. So this is proposed by Airy, Maldacena, Mahajan, and Zhao, where essentially you generalize the quantum extremal surface formula to the non-gravitational region. And what that tells you essentially is that you extremize this quantity, which looks very much like the generalized entropy, except you're including the radiation component in this entropy here. And so the suggestion is that this thing is what computes the entropy and behaves unitarily. Now that's a conjecture, and we like to be able to justify conjectures by explicit calculations. So this leads me to the subsequent developments of the toy models of the so-called East Coast and West Coast models. And I think we owe these names to Don Merrill. So it makes it very easy because there are quite a few authors on these. Now, what is the idea here? The idea is to justify this so-called quantum extremal island formula using this particular two-dimensional model's JT gravity plus something. So in this case, it's JT gravity plus this flat region over here. And in this case, this is JT gravity plus a brane with internal states. And in both of these models, there's a replica trick calculation which is done, or direct calculation which is done, that computes the von Neumann entropy, and it gets a unitary answer. So what's the idea? I'm going to primarily use the East Coast model as just a better illustration for what I'm going to say later. Now, the idea is they take some region R in the reservoir, so this is meant to be the radiation, and define the so-called island that corresponds to, that computes its entropy. And then they literally try to just do the replica trick and see where it gets them, using basically Lukowitz Maldacena. Let me talk a little bit about the replica tricks. So since this is going to be extremely important, I want to emphasize this since I will be introducing another replica trick that computes a different quantity very shortly. So the nth Renyi entropy of some density matrix is defined in this way. And the von Neumann entropy is computed by taking the n goes to 1 limit. Now, from now on, even though up to now I've drawn Lorentzian diagrams, I'm going to now specialize to working in Euclidean signature. So I hope this doesn't cause any confusion. I won't go back to Lorentzian signature at this point. I'm just going to stick with Euclidean signature from now on. So working in Euclidean signature, we can write the state in terms of the Euclidean partition function. And that just gives us the following formula. So this is essentially copied out of Lukowitz Maldacena. This here, z of b, is the partition function on the space B. And z of b sub n is the partition function on b sub n. So b sub n is an n-sheeted geometry that consists of n copies of this manifold B that are cut along R and cyclically identified along R. And if we're working in the holographic theory, for example, so B is our boundary manifold, and we glue these, we make a cut along this region R whose entropy we want to compute. So this is a standard trick that we use. And this is, roughly speaking, the picture. I know this is old hat for many of you. The reason I'm emphasizing this is that it would get confusing due to a second replica trick in a short while. So now that was just a general idea about the replica trick, let's get back to gravity. So again, sticking with the Euclidean case, the idea is that we can replace the partition function by the gravitational path integral. So we start out with z of b, is the partition function. We replace it by p of b. I'll use the script p to denote the gravitational path integral with boundary conditions b. And z of b sub n is replaced by p of b sub n. Again, b sub n is this n-sheeted geometry that's cyclically identified glued along R. So this is the gravitational path integral with boundary conditions b sub n. Now, just as an aside, in the East Coast model, for example, the identified region R is not in the gravitational region. So the gravitational part of the path integral doesn't include this cut R. So basically, it looks like this. This is just ADS boundary conditions for the gravitational component. Okay, so in general, now we're looking at the gravitational path integral. We have p of b to the n. Now, I had b sub n. That was the n-sheeted replicas that were all identified along R. B to the n is just n copies of the boundary of the manifold B. So to the n and sub n, sorry about the notation, it denotes two different things here. So in general, for the gravitational path integral for n copies of the manifold B, it has a contribution from just p of b to the power n, and also connected topologies. Now, there's been a lot of discussion in the past regarding whether connected topologies should or should not be included in the gravitational path integral. I think there's powerful arguments and discussed in this older work here. Now, I think that many of us were of the opinion that these things should not be included in the gravitational path integral because they give you factorization problems, up until it was discovered by the East Coast and West Coast groups that after the page time, the contribution from the connected topologies dominates and precisely corresponds to the new quantum extremal surface that gives you unitarity. So we can include these connected topologies and get unitary evolution of the entropy, which is something that, of course, we've looked for a long time. So should these topologies be included? Well, they result in a unitary page curve, so we want to include them. I mean, usually we say, what do we want? And then we find a calculation that does it. And I guess we can try to ignore everything that's wrong with that calculation. But of course, that's not really the way we do it. And we have to face the fact that including them means that the gravitational path integral on n copies of a manifold B is not the same as the gravitational path integral on B raised to the power n, which gives us a bit of a problem if we assume that the gravitational path integral exactly computes the partition function. Now, there have been a number of different possibilities that have been floated for trying to explain what's going on here and what the gravitational path integral is actually computing. So one possibility that has been discussed in the literature a lot is that the gravitational path integral computes an ensemble average. So this, I'm going to use the bar to really to denote whatever it is the gravitational path integral computes. You can think of it as an ensemble average if you like. There are other possibilities. For example, maybe non-perturbative corrections somehow restore factorization, or maybe its gravitational path integral is just a really good tool for computing quantities that are self-averaging in a single chaotic theory. I think there was a paper from the group at UBC to this effect. So there are a number of different possibilities that can explain what this calculation is really doing and what this thing really is. Now, I am actually going to be agnostic about whether this is ensemble averaging or what else it is doing. My interest in this talk is primarily to understand what are the implications of including replica wormholes in the gravitational path integral, rather than trying to explain what this quantity actually is. Of course, the two are not unrelated in the sense that the hope is that if we understand better what the implications of including replica wormholes are, we might get better intuition about what this thing is actually computing. I will make one comment on ensemble averaging in the next slide, and then I will move on to just, again, being completely agnostic about what this thing is computing, because it's really not important, or it's not a lesson which is important for the rest of this talk. So just an aside on ensemble averaging. So normally what we mean by ensemble or just order averaging is that the partition function is, which I've put in a little sub G here, is defined with respect to some choice of coupling constants that are sampled from some distribution. So this overbar would be some average like so. Now, if this is what the gravitational path integral is computing in gravity, it's really not obvious what an individual member of this is, what a Z sub G is. Now, I think this is fascinating, and again, this is just an aside. I won't subscribe to any particular interpretation of the gravitational path integral in this talk, but it would be nice to have a discussion on this further if anyone in the audience is interested. I think this is a very interesting question. So some questions that we would like to ask. If we want to take these replica wormholes seriously, and we do because we like unitarity, then we need to understand better what kind of calculation the path integral is doing. I would say this is something that we want to understand actually independently of replica wormholes, because the Euclidean path integral is very smart. It knows about the Bekenstein-Hawking entropy, for example, which is not obvious why, to me at least. And so it's something that I think we need to understand anyways, what kind of calculation the gravitational path integral is doing. In the case of the entropy, we would like to know how to actually compute a minus trace rho log rho calculation of the same entropy. So that's what I mean by understanding better what kind of calculation the gravitational path integral is doing. Now, if it is averaging, what is it averaging over? What are the implications of this on other observables? Can we see signatures of replica wormholes beyond the Renyi entropies? For example, we could ask about the generating functional log z or equivalently the free energy minus T log Z. And that, of course, is the main subject of this talk. So that concludes the review. Are there any questions at this point? No questions. Okay. So let me now begin with the replica trick for the free energy. So we want to compute log Z. Now, if the gravitational path integral gets contributions from connected topologies, and again, we would like to think that it does because, or at least, yeah, we'd like to think that it does because that's what allows us to include the replica wormholes in the von Neumann entropy. So if it receives contributions from connected topologies, then in principle, it's possible that there's a big difference between computing this quantity, which is log of this averaged Z, versus the average of log Z. In principle, these could be very different. And in condensed matter systems, for example, this first quantity here is called the annealed free energy, or the annealed generating function. I'll have it written minus T here. This computes an average over the random variables that define a particular instance of the ensemble, which suggests an interpretation that this is a generating functional in a theory in which the variables are allowed to equilibrate. And that's not really consistent with what we want. The second one here, which is called the quenched free energy, this computes an average over free energy of the constituents of the ensemble. So this is an average of the free energies. So it's a situation where the random variables are not allowed to equilibrate, which is much more analogous to what we want. So somehow we want to compute this object rather than this one from the gravitational path integral. Now, even if the gravitational path integral is not computing an ensemble average, so I just put this overline here to denote whatever it is the gravitational path integral is doing, it seems clear that this is the type of quenched, the quenched free energy is the one we care about. But of course, if this average, this Z of B to the N, averaged or computed by the gravitational path integral is not equal to the gravitational path integral of B raised to the power N, then we might also expect that these two quantities, the quenched and annealed free energies, don't coincide either. But of course, we know how to calculate this from the gravitational path integral, but how are we supposed to calculate this thing from the gravitational path integral? Now, it turns out that condensed matter theorists have been doing this for decades. Not from the gravitational path integral, though. They've just been doing averaging. So we can compute log Z via a replica trick. And this is a different replica trick from the one that we do for the von Neumann entropy. So this is a replica trick where we take the replica parameter m to 0 rather than to 1. And this is what it looks like. So it's 1 over m Z of B to the m minus 1. For extra clarity, I will always use n for the parameter of the Renyi. So if we're doing a von Neumann replica trick, and m will always be used for the log Z replica trick. So m indexes the log Z replicas and n indexes the Renyi replicas. So this quantity, of course, we know how to compute from the gravitational path integral. We just plug in p instead of z, and we get this averaged log in terms of the gravitational path integral. So this tells us if we want to compute the log z from the gravitational path integral, this is how we do it. So let's talk a little bit about replica wormholes in the log z replica trick. So if replica wormholes can contribute non-trivially in this m goes to 0 limit, then the annealed free energy, log of P of B, is going to be very different from this quantity here, which computes the quenched free energy. So this one would correspond only to disconnected topologies. We would get only contributions from disconnected topologies. So just this. But in this case, of course, we're taking P of B to the M, which means that we can get contributions from connected topologies or replica wormholes. Now, let me go back one for a second. So one way of making this concrete is saying, okay, let's consider a quantity that we know how to calculate and we know what the answer should be, and ask what do we get. So in particular, let's consider the von Neumann entropy. We want to compute the von Neumann entropy in a holographic theory using the gravitational path integral. Well, really, that means we're going to be computing this bar quantity, and we're going to use our usual Renyi replica trick. But these quantities, really, we should be computing the averaged ones, the ones that are computed with an overbar, which means that the correct calculation involves two compounded replica tricks, one for log z and one for the von Neumann entropy. So really what we should be looking at is this quantity over here. Now this quantity looks clear. This one might be a little bit more confusing. What is meant by P of B sub n to the m is m copies of this B sub n geometry, which again is this n-sheeted replica geometry, which is all identified along the cut R and cyclically identified along the cut R. So this mess here is meant to denote what happens. So this is the n-replicated geometry, and we get m different bins here, so m copies of it. This corresponds to B sub n to the m, this thing over here. And so the correct calculation of the von Neumann entropy holographically really has to involve two compounded replica tricks. And there is one case where it's very easy to see that this makes a difference. So it makes a subleading difference, but it does make a difference nonetheless. So let's imagine computing the von Neumann entropy for a pure state. Now, and suppose that we don't use the log z replica trick. So we're just computing, we're doing log of p of b to the n rather than using the replica trick for that. Now, what happens is that if the replica wormholes contribute at any order, this is not going to vanish identically for a pure state. You're going to get subleading contributions from the replica wormholes. And I think just staring at this makes it pretty obvious. But if we use the log z replica trick, then for a pure state, b sub n to the m is just b to the n times n. And that means that we can rewrite this messy replica trick in this way. We can just relabel the parameters. And plugging this back into the formula for the averaged von Neumann entropy gives us the following thing, which of course is identically 0. And so without knowing whether replica wormholes contribute at any order or not, just including this replica trick gives us the correct answer, which is that the von Neumann entropy of a pure state vanishes to all orders. And so if we fail to include this, then we need to start including corrections at progressively higher orders if the replica wormholes contribute. So this is this maybe is, you could say, oh, this is just a subleading order correction, but nonetheless it's a correction, which suggests that we're on the right track by including this. Now, let's go back to the log z replica trick because it's easier to do just one replica trick rather than two. So just for log z, we don't need this whole mess of the n-sheeted replicas and m copies of them. We just need m copies of the replicas. And we're going to be working with ADS boundary conditions. So when like the East Coast calculation, we don't care about the flat region. Our boundary conditions will just be ADS. And so we just need m copies of ADS, of the ADS boundary, and we will be filling those in. So what is it that we want? Well, we've already seen that the subleading orders, it makes a difference whether we include the log z replica trick or not. But it would be really nice to have a very explicit calculation in some simple theory of gravity where there's a regime where replica wormholes actually dominate the log z replica trick, or at very least contribute at least as much as the disconnected topologies. That would be a smoking gun signal that we really have to include this in log z, that the replica trick is really important. Now, in JT gravity, and there have been also some other studies, there have been numerous studies of the lack of factorization due to contributions of these connected topologies to BB to the M, PB to the M. So if we take this and we just do 1 over M and do a -1 here, then clearly those connected topologies should also contribute to this expression. But so far that's easy, but it's easy given the work of these authors. But the M goes to 0 analytic continuation is actually pretty subtle. And remember, we need to go to M goes to 0 of this thing. And M goes to 0 is a confusing limit, and as it turns out, something much more interesting actually happens when you take that limit. So that brings me to the calculation of the free energy in JT gravity. Are there any questions so far? All right, moving on. So in my experience, there are 2 different kinds of audience members. The audience members who just want the big picture and to be told what the general upshot is and to not see the calculations. And there are some audience members who just really want to see the calculations. So in the hope of making both types of audience members happy, I'm first going to give the big picture and generally what we found. And then I'm going to go through some of the details Not too many technicalities, but hopefully enough to keep the second type of audience member happy. So let me begin with the big picture. What is it that we see? What did we find? So the long and the short of it is replica wormholes give a larger contribution to log Z than disconnected topologies at low temperatures. So this is the basic tagline here. In fact, if you didn't know about replica wormholes and you just said, I'm just going to compute the annealed free energy, just using disconnected topologies, you actually end up getting an unphysical free energy. And I'll say in what way it is unphysical. So if that's all you calculated and you didn't know about replica wormholes and you didn't think about them, then you would still know that you have a problem. So it's clear that the annealed free energy is not the full story. The disconnected topologies cannot possibly give you the right answer. Now, the pathological behavior, at least prima facie, appears to be mitigated by the inclusion of replica wormholes. So you start seeing behavior that's progressively better as you include more of these connected topologies. But unfortunately, we can't do the calculations sufficiently to sufficient high order to show that this is sufficient. It's not obvious that this is sufficient. Even with the inclusion of replica wormholes, at least to the extent that we can include them analytically, and a resummation of the genus expansion, the free energy still appears to be non-monotonic with temperature. So this is this pathological behavior that I was discussing here. The free energy is non-monotonic with temperature, which means you have a negative entropy. So what is going wrong here? Well, okay, one possibility, a boring possibility, is that the pathological behavior actually is completely mitigated by the inclusion of replica wormholes, but you just need to work to progressively higher orders, and I'll say what I mean by that. Another possibility, something that can go wrong, is the analytic continuation itself. It turns out that in this case, there actually is a lot of freedom on how to do the analytic continuation, which is different from the von Neumann entropy replica trick, at least in certain cases. And the obvious or simple analytic continuations are just, they're not the right ones. Now, the interesting thing is that this has some parallels to replica symmetry breaking in spin class systems, where you have a similar situation that the free energy is pathological if you just consider these disconnected replicas, but you consider the quenched free energy, you consider the connected replicas, and there is the situation is that a naive analytic continuation ameliorates the problem, but it doesn't fix the problem. And you need to introduce replica symmetry breaking in order to actually completely fix the situation, this pathology. So the main takeaway is that in at least some low-dimensional theories of gravity, there exists at least one regime in which replica wormholes have to make a large contribution to log Z to avoid various pathologies. And this contribution most likely requires a highly non-trivial analytic continuation that has some parallels to spin glasses. So if you can only take one thing away from this talk, let this be it. And now I'm going to tell you in more detail what we actually did. I think I have time for that. Okay, so let's go into a little bit more of the details. And I should say, I'm going to only talk about JT gravity, but we actually also did an analysis of a certain simplified model of CGHS if you wanted to take a look at it. And that's, in that case, actually everything is a lot simpler. Okay, so here is the JT gravity Euclidean action. We have the topological term, and then we have the dilatant boundary term. And what we're interested in, of course, are boundary geometries that connect, the geometries that connect M boundaries of certain length. So the path integral over these geometries that connect M boundaries with length B was fortunately computed by Saad-Chan for Stanford. And this is the notation that we'll use for it. So this means the path integral that connects M topologies, or M boundaries, with length B. And this is the formula for it, where ZG sub M, this is a function on the volume of moduli space of constant negative curvature spaces, so the so-called Weil-Peterson volumes. And these are with M boundaries in genus G. So these things are polynomials in beta, beta here being the inverse temperature of this order. So just as an example, if we're just looking at two boundaries and of length beta, so we have this first contribution here, and then we have an additional handle or two additional handles and so on. Now, the connected topologies are suppressed at large S naught. And a simple analysis actually shows that the connected topologies compete with the disks precisely when beta to the 3/2 e to the minus s naught is order 1. So that's a regime that we, of course, immediately zeroed in on, because that's a regime where we might say, okay, here we have a chance of the replica wormholes dominating. Now, if you're us, we totally raise a concern here. You might raise a concern here, which is that you appear to need the main parameter of the problem, which is beta, to be non-perturbatively large in S naught. Now, this might raise two concerns for you. First is that the connected topologies can only dominate in a regime which requires non-perturbative physics. So you might worry about something like that. But this is no different from the von Neumann entropy case, where really what you need is the size of the Hilbert space of the radiation to compete with e to the s naught. So if we're thinking in the West Coast model, this parameter k had to compete with e to the s naught. So you need something non-perturbative, but that doesn't mean that you lose control over the problem. The second concern you might raise is, well, don't you lose control of the problem? The genus expansion is asymptotic at low temperatures. So don't you actually have this problem where you can't keep track of the genus? Well, it turns out that there actually is a separation of scales. So there's an intermediate regime where the connected topologies dominate. Temperatures are not so low that the genus expansion is out of control. And so you can do a partial sums of the genus expansion in the regime where it gives you a good estimation of what the S series actually is. And there is a regime where the replica wormholes are important and the genus expansion is quote unquote well behaved. And moreover, in a certain limit, the so-called Airy limit, we actually can sum the genus expansion exactly, and it doesn't change the behavior. So hopefully this alleviates these two potential concerns. So let's begin by looking at the annealed free energy, since I claim that that's problematic. Excuse me. So again, the annealed free energy is given by log of P sub B, of P of B. And we can just compute this purely from disconnected topologies. So here I'm showing partial sums of the genus expansion. And ignore the red for a moment. I'll explain what it is in a second. So this blue here, these curves correspond to progressively higher genus. And as you can of course see, this is not very well behaved at very low temperatures. But notice that as you go to somewhat higher temperatures, maybe T greater than or equal to 0.3, these are appearing to converge. And all of them are non-monotonic. So the annealed free energy appears to be non-monotonic, but this appears to be a robust feature that's non-monotonic with temperature. And since the entropy is minus dF dt, this means a negative entropy somewhere, which is unphysical. So again, if you didn't know about replica wormholes, you might look at this and say something is wrong. I don't know what, but something is wrong. This log of QB clearly does not compute the free energy. So let me say a few more words about the genus expansion. If you're not worried about it, if you accept my explanation, you can sleep for the next couple of minutes. But if you are worried about it, please do listen. So, what's going on with the genus expansion? It's a little bit complicated. You can try to do two different things. You can do a partial sum analysis. So here, these are these partial sums. And again, at very low temperature, this expansion is very poorly behaved. But again, there's an intermediate low temperature regime where the asymptotic series is under control. And the partial sums are a good approximation for what the series is actually doing. And the non-monotonicity is in this regime. It's not in this very poorly controlled regime over here where we really cannot trust the genus expansion at all. So that already suggests that this non-monotonicity is here to stay, even if you resum the genus expansion. Now, this red line over here is actually working in the Airy limit. So in the Airy case, what you do is if you take S naught to be large and TE to the 2S naught over 3 fixed, then it turns out you can actually exchange the asymptotic genus expansion for an expansion at low temperature. And that expansion you can actually sum exactly. And this gives you the red curve. So the red curve is exact. And as you can see, it's very much non-monotonic. And this tells you that genuinely there is a problem here. This free energy is non-monotonic with temperature, and therefore the annealed free energy is just completely unphysical. So either way, whether we choose the partial sum method or we just limit to the Airy case, we find that the maximum is robust against adding higher general. So, okay, so we say we've ruled out the annealed free energy as the correct free energy. So that means that we have to get significant contributions from replica wormholes if we're taking that the quenched free energy, if we want to take the quenched free energy instead. Now the quenched free energy again involves this taking this quantity and analytically continuing to m goes to 0.
2 bald eagles over ons balkon.
Niet.
Ja, kom.
Sorry, what was that? Is there a question? I'm
Someone had
gonna
their mic left on accidentally, so
All right.
they're muted now.
Okay. All right. So we can't compute this analytically as a function of m, even though that's what we would need to do to take the m goes to 0 limit, because the ZGMs, which I had before, so these are, go back up. Oh, so these ZGMs are not known analytically in m. They're known recursively. So you can compute, knowing one, you can compute the next and compute the one after that, but you don't just have an analytic formula for them in general. So we can't just literally do the analytic continuation, but what we can do instead is define what we call a truncated path integral. So this we denoted p little m comma big M. So the idea here is that this thing takes it takes m boundaries, little m boundaries, and connects up to capital M of them by an iterative procedure. So here's an example, p12 comma 4, meaning there are 12 boundaries involved and up to 4 are connected. So this receives contributions like so. And then we get this one plus p4 comma 3. We have 4 boundaries, up to 3 are connected, plus this, and then 8 boundaries, up to 3 are connected. And then this one, which is 12 boundaries and up to 3 are connected. So we have this iterative procedure, and the quenched free energy is given by a double limit. Capital M goes to infinity, little m goes to 0 of this p little m capital M. And so for a given m, for a given capital M, we can analytically continue to m goes to 0. So let's see what happens. So here we did this calculation for m equals 1, 2, 3, 4, and 5. The blue curve is m equals 1. M equals 1 is just the annealed case because that's just disconnected topologies, right? Capital M is the number of boundaries you're allowed to connect. So if m equals 1, then these are all disconnected. So the blue curve is very non-monotonic. Now, as we include more and more of the m's, it sort of looks like the non-monotonicity might be getting milder. It's not clear that it will save us. Now, this is for a particular choice of analytic continuation to m goes to 0. I can do another one. So here are 2 different analytic continuations to m goes to 0. And the reason that we can take 2 different ones, they're qualitatively similar, but quantitatively they're different, is that the analytic continuation to m goes to 0 is actually not unique here. So that's somewhat unusual. It's not something that we usually encounter, but it is what happens. Now, we know that in both of these, we get this non-monotonicity. Now, again, it's not impossible that when we take m goes to infinity, the naive analytic continuation that we did the first time might actually work out. But it's not obvious that it does. It's not clear that this is actually going to resolve this non-monotonicity. So if it does not, then these 2 analytic continuations, neither one of them is correct because we have this non-monotonicity. So we've learned that replica wormholes must contribute, but it seems that they have to do so in a non-trivial way due to the very non-uniqueness of the analytic continuation. So we have to find the right analytic continuation to do here. Without some top-down derivation, without some non-perturbative calculation that tells us exactly what it is from quantum gravity, we can just try and guess what the right analytic continuation is. Now, some of you might be wondering, what about Carlson's theorem? Usually Carlson's theorem is the really nice theorem that we always invoke when we use the replica trick to say, the analytic continuation is unique, so we don't have to worry about taking n goes to 1, even though it might sound kind of shady. So what about it? I just stated Carlson's theorem here. So Carlson's theorem tells you essentially if you have a function which is analytic for the positive reals, and it grows more slowly than sine of pi z on the imaginary axis, no faster than e to the z elsewhere, and it vanishes for the positive integers, then it's identically 0. The way that we normally use the Carlson's theorem in the replica trick for the von Neumann entropy, for example, is we say, suppose we have 2 different analytic continuations. We let F be the difference between the 2, and then we use Carlson's theorem to show that F has to be 0. So therefore, there's a unique analytic continuation. But in this case, the increase with M is actually super exponential, which means that we violate the basic assumption of Carlson's theorem. It doesn't apply, and we do not have any guarantee that the analytic continuation is unique. And in fact, we see it's highly non-unique. So somehow we have to find some principle that tells us what the analytic continuation is. And I want to emphasize that I think it's really important, because I think whatever the analytic continuation is, it's telling us something important about quantum gravity. This is the gravitational path integral, is computing the generating functional, and the correct value of it is telling us exactly how the analytic continuation has to work. So let me make an analogy here now with spin glasses, actually. So as I mentioned just now, finding the correct analytic continuation is clearly very important for understanding the gravitational path integral better, which in turn, of course, informs us about various different aspects of quantum gravity, black hole information paradox being one. Now, there's a very tantalizingly similar story in spin glasses. So in spin glasses, if you compute the annealed free energy, basically this is its behavior as a function of the temperature. So this looks very, very similar to our annealed free energy as a function of temperature. Now, if you include correlated replicas, so the spin glass analog of replica wormholes, they improve the situation. That's this blue curve over here, but there's still a non-monotonicity, so they don't resolve it entirely. Now, the resolution in the spin glass case is something called the Parisi ansatz, which is an analytic continuation that involves multi-step symmetry, multi-step breaking of the SM replica symmetry, so the permutation group replica symmetry. Now, I'm told that there's forthcoming work by Clifford Johnson that suggests that you don't necessarily need replica symmetry breaking in JT gravity, but there are certain non-perturbative effects that may remove the need for replica symmetry breaking. So in other words, they may give you the correct analytic continuation. Now, the analog with spin glasses is tantalizing, but I would say so is the idea that non-perturbative effects could remove the need for replica symmetry breaking altogether. As an aside, there are also certain studies of low energy effective field theory of SYK that have also found replica symmetry breaking. Now, it's not immediately obvious, given the limit that they work in and the limit that we work in, that there is a connection, but it is a tantalizing possibility. Okay, so I think I will be right on time. Let me summarize and make some comments. So recent developments on the black hole information paradox have suggested that replica wormholes should really be included in the gravitational path integral. That's because we like unitarity. Now, one way of interpreting this, of course, not the only one, I've mentioned at least 2 other ways, is that they're computing, and the gravitational path integral computes an ensemble average. Now, whatever is the interpretation, we'd like to understand how general it is as far as higher dimensions go, for example. I think many of us would like to understand how this works in n=4 super Young-Mills. Now, we would also like to know how to calculate everything that the gravitational path integral computes without using the gravitational path integral. So, for instance, we would like to be able to compute the fine-grained entropy of the correct state, whose entropy the gravitational path integral computes in the quantum extremal Island formula. I would like to write a minus trace rho log rho equals quantum extremal Island formula. All of this means understanding the gravitational path integral better. And in my opinion, this is sort of the single most important thing that we should be working towards right now, at least one of the most important things we could be working towards. Now, in this particular paper, we were interested in probing the replica wormhole phenomenon in the gravitational path integral by looking at what you might call a more primitive, a more fundamental quantity than the von Neumann entropy, which is the generating functional. And in JT gravity, and I should say also in CGHS, although I didn't have a chance to talk about it here, we find that at sufficiently low temperatures, but not so low that the genus expansion is out of control, the free energy without replica wormholes is severely pathological. So this cannot be the right answer. Now, it also appears to be pathological with replica wormholes, although there are multiple outs. One potential possibility is that we have to just take the m goes to infinity limit. But even in that case, because the analytic continuation is so non-unique, it's not clear what the correct or even intuitive one is. This has a lot of similarity to spin glasses, where a novel analytic continuation removes the pathologies altogether. So a few comments on outlook. I think figuring out the correct analytic continuation seems extremely important and probably telling us something very interesting about the gravitational path integral. Now, unfortunately, the analogy with the spin glass, and I think the word analogy is quite strong, we really should be saying the parallels with the spin glass, is not sufficiently informative at the JT level. The reason is that in spin glasses, we need to work in the saddle point approximation. So that's how everything is done in the saddle point approximation. And in JT gravity, we compute the full gravitational path integral. So it looks like we have a bit of a conservation of misery situation where it looks like we need a more complicated theory of gravity for this analogy to really work out. But if we do that, then we have way worse control over the gravitational path integral. So we have to work around this conservation of misery issue. Now, I haven't really talked about spin glasses, but let me push the analogy maybe to a breaking point. In spin glasses, well, I won't say what it is in spin glasses, but I'll just say what the suggestion is. There's a suggestion that the metric may be emergent purely as a consequence of ensemble averaging. So potentially the metric is emergent as a mean field. And I wanted to ask if this is informative quantitatively about space-time or geometry emergence in any way. And it's not clear what exactly is the content of the analogy with spin glasses until we can do a saddle point analysis in gravity, and whether that analysis will show that the parallels continue to hold. But in spin glasses, at least, you have several features that show up basically as a consequence of ensemble averaging. It will be interesting to see if the metric is similar in gravity. And of course, I think one of the most interesting questions to ask is if there are any other regimes beyond low temperature, even in JT gravity or JT plus matter, where the replica wormholes dominate the free energy. So with all of this food for thought, I will end here, and thank you for your attention.
Okay, let's thank Netta and do some audible clapping. Any questions for Netta?
I just had a clarification question about the proposal that you mentioned of Clifford Johnson. So he's suggesting that some non-perturbative effects come in. I guess I might have thought that would be sort of associated with some perturbative expansion breaking down. I'm wondering if, so you mentioned these two different scales, one where the replica wormholes start showing up and one where the genus expansion breaks down. And
yeah.
I mean, is the suggestion that these non-perturbative effects are already important at the first place?
So I would be completely honest, which is that I heard about Clifford's work a couple of hours ago.
Okay.
And I thought that it would be dishonest not to pre-cite it in this talk, given that it's an alternative to replica symmetry breaking. So I didn't want to tell you guys about, I think it's all a replica symmetry breaking when there's a potential alternative. Unfortunately, I don't think Clifford is here, but I'm going to refer these questions to him and to the upcoming paper. I wish I had more information. I personally would really like to know as well, but unfortunately I don't, yeah.
But the correction needed are small, so it's kind of plausible that, you know,
sorry,
even in the regime where this converges and the non-perturbative correction are small, they might still save you.
They might, yeah. It's especially, it could also be a situation where several different things sort of come together. So it's possible that the m goes to infinity limit is much better behaved than any finite m, where you almost get rid of the bump altogether, and maybe some additional very small non-perturbative effects, and just enough to fix it. Yeah.
But what would replica symmetry breaking look like in terms of the wormholes?
Yeah, so that's a really good question. It's very difficult to try to visualize how that would behave, because so in spin glasses they don't have the wormholes; they just have correlations between replicas, and they have this permutation symmetry group, and then they just find that the symmetry group is broken, and it's difficult to visualize, yeah, what that would look like. Yeah, I wish I had a better idea. That's part of what makes the problem so difficult. If I could write down a Parisi-like ansatz in gravity, I would have done it already.
Yeah. Well, the geometrical picture might not carry through though, so it's yeah.
Yeah, I mean, you couldn't.
Yeah.
I wish it's very hard to visualize. It might be something completely non-perturbative where it doesn't really have a good geometric picture, but you just weight different types of wormholes by different amounts. And it's pure speculation. I really don't know.
Ask probably the same question, but if there's anything that would be like an order parameter for the replica symmetry breaking that you understand, but I think that's probably the same thing Moshe was asking.
Sorry, was that a question, or you just I missed out there?
I wondered if you had any ideas about what sort of an order parameter for the replica symmetry breaking would be, but it's probably just goes back to the question Moshe asked.
Yeah. So the thing is, in order to really what we really want is an order parameter. You're right, and it would be a lot easier if we were working in a saddle point approximation to identify the order parameter. In working with the full gravitational path integral, it seems like we just don't have it. So JT gravity, I think, falls a little bit short of what we want if we want to really pursue this parallel with spin glasses and replica symmetry breaking. So I mean, the natural thing to do now is to try to look at higher dimensional gravity, where we can work with the saddle point approximation, and see if we can identify this, if we can figure out what this looks like there. And if there are some simplifying assumptions where we can actually do some saddle point approximation, even in 4-dimensional gravity, for example.
So you have large n, that's not enough. You need actual infinite volume as well.
Yeah, so here, for example, we compute all these Weil-Peterson volumes in order to, or we look them up, we don't actually compute them.
Right.
Yeah. So we would have to do something analogous. We would have to do something analogous in higher dimensional gravity. Of course, not doing the full gravitational path integral, because that would defeat the purpose.
Yeah, no, I mean, why? So you know, all of those things in spin classes are only well defined in the thermodynamic limit, but usually in gravity, you say you have infinite n, and that's your excuse to do things that are thermodynamic in character. Is that not enough in JT?
It's not in. You mean it's not enough in JT to work in the saddle point approximation? Is that what you're asking, or?
I'm saying. Oh, okay, so maybe you have too much. I'm just saying, generally, I think in the replica symmetry breaking or any other symmetry breaking is only well defined strictly in the infinite volume limit.
Oh, but are you thinking of the replica symmetry breaking for the von Neumann entropy?
For anything, I think any symmetry breaking at all is only well defined mathematically in the infinite.
Oh, I think I see what you're saying. Yeah.
Yeah. So why is the large n not enough here? That's usually the excuse. I mean. So if you take strictly large n, would those concepts become, more precise, sharper?
So certainly I'm not claiming that the replica symmetry breaking isn't there. It's just we don't a priori see how to find it. It's not that it's not well defined. I think we just don't. The replica symmetry breaking is in the correct analytic continuation, and without additional information about sort of some kind of a top-down quantum gravity model, we don't really know what without additional information, we just don't know what the right analytic continuation is.
Yeah. I'm just confused why you need a higher dimensional model specifically.
Because working in JT gravity in a saddle point approximation is trivial. So we want to work with this in a situation, if we want to really try to just basically do a spin glass analysis in gravity, then we need to work in a saddle point approximation.
I see. Okay. Would ADS3 gravity be enough?
It might, yeah.
Yeah, I was wondering if, so there's some version of replica wormholes that appear in gravitational computations of like either the if you look at the 2 interval entanglement entropy, then this phase transition that appears, one can sort of understand that in terms of the gravitational path integral, and Faulkner's computation sort of had something like replica wormholes showing up, and I was just trying to think if there was some analog of what you're doing here that is or starts from that story.
So I think that what you're referring to is this. So there's been a slew of recent papers about the replica symmetry breaking, specifically, I think, in those cases where you're near a transition. In the holographic case, right? Where they have two different intervals and they sort of look at replica symmetry breaking there. Mm-hmm. But it's replica symmetry breaking for the von Neumann entropy.
Right.
And that's not as a result, if I understand it correctly, that's not really as a result of the n goes to 1 limit. I think they see that already for the Rennies. That's a breaking of the Zn. Here, this is a replica symmetry breaking that sort of appears spontaneously as you take the n goes to 0 limit. Sorry.
Yeah, I guess maybe more generally, I'm wondering if there's some setup in the context of 2D CFTs that would be similar to what you're talking about, but give another slightly more complicated example.
Yeah, so I can say that my intuition on, maybe this is sort of relating to this third bullet point here, is that in regimes where you're sort of on the cusp of a transition is precisely, those are regimes where you might see replica wormholes mattering in the free energy. And I think that's a really good place to look for those signatures. And it is, I would say it's promising if there's replica symmetry breaking in the von Neumann entropy, because it suggests that there is, I would say intuitively that suggests there's a potential for replica symmetry breaking in the free energy. But especially if we're looking for the replica wormholes in the free energy, I would guess that in situations where you're on the cusp of a transition, near the page time, right at the cusp of the two intervals, those are places where we might want to look for replica wormholes into free energy.
Coming back to the question that was raised by James regarding the definition of an order parameter here, would it not be natural to take the root mean square of the sum of the squares of the wormhole, that is the number of wormholes? I mean, I'm just working by analogy with the Edwards-Anderson order parameter.
The number of, sorry, what do you mean by the number of the wormholes?
Well, you have an expectation value for the number of wormholes. Well, rather, it's actually the density of wormholes that you want. Okay.
You could imagine taking that. I think that that requires a better control over this, the analytic, the function 1 over m p of b to the m minus 1 analytically in M.
Yeah.
Which we just don't have. That's part of the problem here. We don't have analytic control over that, so we're forced to make various approximations, which might be the problem here.
I haven't any comment on that, sorry.
I mean, maybe just infinite volume, low temperature in two-dimensional CFTs. That seems like the natural next thing to guess.
Sorry, Moshe, can you one more time?
I'm just saying the natural place I would guess is infinite volume, low temperature in two-dimensional CFTs. It's just seems like much of what you guys did should be fairly similar. Yeah, I don't know.
It seems to me that potentially working in the CFT first to find looks for signatures of this might be very informative about what we expect on the gravity side. Yeah.
Yeah. I mean, there's a limit of IDS3 that gives you back JT, so maybe around
That's
there.
right.
Okay, interesting.
I'd say 3D gravity is probably a good place to look at because, but there's some suggestions that there might be an ensemble average there as well, and so it's in some sense it's quite similar to JT, and we see this phenomenon in JT, but we can work in a saddle point approximation is not trivial. So there's a sense in which it might be the best of both worlds.
Yeah.
Maybe if there's any last question for Netta before we let her go. Okay, well, let's thank Netta again. I'll do more audible clapping for everyone.